Alright guys, today we're going to be covering the operation and the diagnostic of heavy-duty heating, ventilation, and air conditioning systems. Yay, super excited, right? Um, we've already talked kind of a little bit about kind of the standard, how they work. Now we're going to get more in detail as far as how to actually work on them and how to know what we're working on. Let's move on to safety. So first and foremost, when you're working on an AC system, AC systems are always under pressure. Not always, I suppose, if they have a loss of freon, they're not. But still, you ought to pretend or at least assume that they're always under pressure. That means whenever you crack a line, something like that, just like in any system under pressure, it could explode out of there, cut you open, anything along those lines. On top of that, you should never really come into contact with Freon. It's a heavy irritant for skin, eyes, you name it. I'd say probably one of the biggest things that could happen is you could freeze yourself. It will actually give you frostbite, nasty frostbite. So be a little careful. For example, here, take a look at this. Show you some pictures. I know you probably don't want to see them, but I got them here for you anyway. That way you can see just what you don't want to do. There you go. There's some good examples. Thanks to our Google picture person for volunteering some pictures for us. You don't want refrigerant to come into open flame, especially if you're working with the new refrigerants. Some refrigerants are flammable, so you could cause combustion, all kinds of fun stuff. Even when they're not flammable, they can put off poisonous gases you don't want to be breathing in if they catch on fire. They could cause a lot of irritation. Oh, the Clean Air Act regulations. All right. Refrigerants must be recovered and recycled by all users to protect the environment and should never be released into atmosphere. Under these regulations, service facilities not having the required recovery and recycling equipment and properly trained and certified personnel are not permitted to perform any refrigeration service work. We kind of already covered this in the MAX certification training and test. Basically, if you don't have the proper equipment and if you're not certified, don't work on it. That simple. That's the point of this class, get you certified. Hopefully your shops have the right equipment. Never pressure leak a test of R134A with air, shop air. Do not charge a system with shop air. I was looking for a YouTube video to show you guys and ended up making my own simply because I saw a guy literally compress his HVAC system. He tested it. There was no HVAC or no Freon in the system. He went ahead and compressed it with air. Extremely dangerous. You never really know. Could become combustible. Watched a few other videos. They all did stupid safety things. So I finally ended up making my own. This is one example right here. Don't compress it with air. It could combust and blow up. As you can assume, HVAC is designed to keep a vehicle at a comfortable temperature. A lot of this is kind of a little bit recap. Also meant to clean the air, so in other words, condition the air. So as it's going through this is our evaporator right here. As it's going through the evaporator will pull in the moisture. It'll pull in the heat. That is known. The moisture just drains off the fins, comes out the bottom. There's a little rubber grommet down here that it drains off into. But then pollen and dust is also collected a lot of times on the back side of the evaporator, on the front side of the evaporator, I should say. Right here, there's a little fiber filter. It's designed to catch all the dust, all the pollen, all the stuff like that. If that filter ever plugs up, especially if you get into an AC system that's blowing hot and it's obvious that the owner has pets inside of their vehicle, you definitely want to check that filter. A lot of time pet hair will build up on that filter, plug it all up, and then it won't get the proper airflow, and then you have hot air blowing through, or no air blowing through. Once again, a little more recap. Thermodynamics, study of heat. Heat travels from hot to cold. That's probably the most important one of all of them. Heat travels from hot to cold. Latent heat is heat energy required to change a substance from one state to another. Inside of an HVAC system, we are constantly changing state of the freon from liquid to gas to vapor to so on and so forth. So understanding that heat is released, when heat is released and when heat is needed or obtained. So inside the evaporator, the freon actually absorbs heat in order to change into a gas, and then in the condenser, it releases heat in order to change into a fluid. And then we got BTUs, standard measurement for how much heat energy is needed to raise 1 pound of water. I think we got that on the next slide, but we've already kind of talked about this, right, guys? Here's our latent heat absorbed as liquids go into vapor, latent heat being released as it's going back to a liquid. All of this was in some of the previous videos. Hopefully you should have already watched. Pressure and heat. The temperature at which a liquid boils depends on the pressure acting on the liquid. Decreasing the pressure allows or lowers the boiling point, whereas increasing the pressure raises the boiling point. Once again, this comes in with our state of change, as well as also when we're evacuating a system. So we're pulling all the freon out of a system. Over time, water can kind of build up inside of a system. And that's not exactly a good thing because water freezes into ice, plugs up the system, causes the AC system to go down. So when we vacuum all the freon out of a system, we actually put that system into a negative vacuum and we hold it there for quite a while. And the whole point of that is to lower the pressure so much that the boiling point rises and all the water that is in the system becomes a gas and therefore is able to be vacuumed out safely. Once again, some main principles. Heat moves from hot to cold. When liquids are heated and evaporate to a vapor state, heat is absorbed. When gas condenses, vapor to a liquid state, heat is released. Those are the big ones, right? All right, let's talk about a truck system. So this is your standard truck system. Got a condenser right up here on the front. Well, let's start at the compressor. Compressor builds up pressure, high pressure line coming down here to our condenser where it's cooled, where the heat is released. Comes out of the condenser, goes through our receiver dryer where it's dried, all the water's collected, any big particles and stuff gets collected down in here. Once again, this is still a high pressure line, so if you ever see this thing freeze over, then you know for a fact that thing's plugged up because high pressure lines are always going to be hot. We'll talk about this a little bit later, but you're going to be looking at about 110, 120 degrees in this inlet line. You're going to be looking at about 80, 90 degrees in this outlet line, all the way up here to the expansion valve. And that's when you finally get the changeover from high pressure to low pressure because the freon's traveling through an itty bitty tiny little orifice there. And so as it transfers through, it's got a backup of pressure here and very low pressure on the output side of this evaporator. And so you're going to have a transfer of heat, not a transfer of heat, a change in the heat. It's going to be cold now on the low pressure side of this expansion valve, where it'll be cold going through the evaporator, coming back out, all low pressure, low pressure, low pressure until it gets to the compressor, where it then builds up pressure again and gets hot on the output side of the compressor. Same thing, better view. High pressure, hot line, 110 degrees, 120 degrees, goes through the condenser. On the output side, you're going to be looking at about, somewhere around 80 degrees. The reason I talk about this is because if you are using your hands to diagnose this system, you think this system's plugged up. Knowing these temperatures is a good way to be able to diagnose it. You can either use your hand or you can use a thermometer or something to get these temperature readings and be able to know if you ever have a massive temperature differential, then you know for a fact where that plug is. Goes to the receiver dryer, dries out. This is desiccant right in here, dries all the water out, as well as you're going to have a couple of degree drop here as well. Gets down into the H block. This is that tiny orifice I was talking about. So you got high pressure here, low pressure over here. Goes through the H block, travels through the evaporator, On the other side of this H block is our control, but we're going to talk about that once we actually get into H blocks. Low pressure, low pressure, low pressure, back up to the compressor, and the compressor then obviously compresses it into high pressure. All right, so there's a few different types of compressors. You have your piston, your vane, and your swash plate. Pretty much you guys should already understand these. They're a simple pump. One big difference is you got your compressor clutch up here on the front. This clutch is engaged electronically. It's got a magnet inside of there that engages that clutch on the pulley, which drives the compressor. It's belt-driven pulley. But we're going to go ahead and do a quick review over the different types of pumps. So our first one we're going to look at is going to be our piston pump. Standard piston pump, you got a couple reed valves in here that allow flow in as the piston's going down, and then only allow flow out of this side as the piston's coming up. Pretty simple. Inlet, outlet, couple reed valves, couple different directions. Here's a cutaway of the piston stop. So sometimes you can have a couple pistons in here. It just depends on make, model, stuff like that. Here's our compressor clutch assembly I was talking about up here. Right here's our magnet down inside of there. Pistons go up. Here's our reed valves up inside of here. Actually, those weren't reed valves, but they were valves all the same. Vane. Hopefully from hydraulic class, you guys kind of remember how this works. Rotates around. Got our suction port. So the Freon comes in here in a suction, right? Because it has basically zero, I keep wanting to say mass, not mass, volume right here, right? And so it's expanding and this volume is getting larger as this rotates around. That causes that suction to pull in the Freon that's out here, pulls it in, comes around, ends up getting compressed down on this side and discharged out. Cutaway of a rotary vane compressor. I think you've all kind of seen vane pumps. You've seen piston pumps. This is nothing new. Once again, swash plate. You've seen one of these as well. The big difference between this swash plate and maybe some of the ones at least that you viewed in hydraulics classes, this one is not an over center. So there's no reason to actually run the AC system backwards. So we don't need an over center here. But we do have a swash plate that allows more control of how much pressure we want this compressor being pumped out, so that you can actually move in some of the swash plate compressors. You can actually change the angle if you're not wanting a lot of pressure and leave it in a constant drive. Not very common. They still like to use a clutch. They still like pull on for the most part, but the fancy dancy super expensive ones, they do have swash plates that are adjustable. When compressors come in, so you pull one off the shelf, they come in with what's known as shipping oil. A lot of compressors, they'll actually have a stamp on the compressor itself saying, hey, drain this oil out. This is shipping oil, put new oil in. When you do that, drain the oil out into a measurable container. That way you know how much came out, and you put that exact same amount back into that compressor before installing it on the truck. Here's our compressor clutch assemble. So here's our field coil. This is our magnet that engages it. Pulleys. Here's our belt drive pulley. Here's the actual clutch hub itself that gets retracted down in there, which drives the pump. On to condensers. So a condenser is where we get a state of matter change. The compressor's job is to build up the pressure. The condenser's job is to give it the freon the compressor's job is to build up the pressure of the freon. The condenser's job is to not cool the freon, but to allow a place for the freon to release its heat. As it releases its heat, we really don't care how much heat it loses as much as we're still getting the state of change. So this is very important, basically because the compressor itself cannot take a liquid, so we need a gas going through the compressor. However, we do want a liquid coming out of the condenser itself, That way, as it reaches the evaporator, it has something to expand into. Um, so it goes back into a vapor or back into a gaseous state when it attracts that heat in that's at the evaporator. Now, across this condenser, we're going to lose somewhere around 20 to 50 degrees Fahrenheit um, because we're releasing that heat out into the atmosphere. If you're only losing about 20 degrees Fahrenheit, a lot of the times what that means is these fins right here are plugged up with dirt or debris or bugs or anything along those lines. So go in there, clean them out. Hopefully you can get that up to 30 or 40 degrees difference. It doesn't always mean if you're reading 20, it doesn't always mean it's dirty. It's a good indicator that it probably is. So go in there, clean it out. Hopefully you lose a few more degrees and you can move on. If you see an 80 degree or 100-degree difference, well, it's probably plugged inside of that condenser because you're going from high pressure to low pressure inside the condenser itself. So something's plugging it, not allowing the full freon flow to go through, and therefore you're getting the pressure change. Receiver dryer. This is on the receiver dryer, not the older accumulator side. The accumulator side is typically on the low side. So it'd be over here in this low pressure line, and we'd have an accumulator tube in here instead of an H block, but we'll get to that once we actually start talking about accumulators. This is a receiver dryer on the high side. Its entire job, it's full of desiccant right down in here. Its number one job is to get rid of any moisture that's in the system. It'll also catch some larger particle debris, things like that down in the bottom. You got a little bit of dirt or metal or something inside of there. It's supposed to catch it down in here. Like I said, it's on the high pressure side. If anything that's in this red to orange area is ever frozen over, then you know for a fact you got a plug wherever it's frozen over. Simple fact is, it should always be hot. So if it's frozen over, it's not, it's plugged. Here's a little bit better picture. Here's our desiccant down inside of here, flowing in, moving out. It also does store some refrigerant. It is kind of used as a little bit of a more or less battery pack for the Freon system. The accumulator works a little more off of gravity. So in other words, if we look at this coming in here, we got water and dirt particles coming in. Those water and dirt particles are going to drop down to the bottom where this is in the low pressure side, right? So this freon's a gas, is able to float and escape through this tunnel through up here. All right, let's look at the different types of HVAC systems. The first system we're going to look at is the orifice tube. All right, so this is the older system. It's probably the least likely system you're going to run into, but it does exist out there. It's pretty simple. So out of all the different systems we're talking about, I'm going to refer to orifice tubes, H blocks, thermal expansion valves, all of those as kind of a gateway. So we have our compressor here. That's one gateway because it goes from low pressure to high pressure at the compressor. The orifice tube or the H block, if we had an H block right here, I consider the other gateway because that's where we go from high pressure down to low pressure. And the way the orifice tube does that is we have an itty bitty tiny hole right inside of here, right? That tiny, tiny, tiny little hole inside of there basically doesn't allow all the freon to flow through it. So in other words, you're going to have a pressure change because it doesn't have enough volume, a big enough hole to allow enough volume through, so the pressure builds up on the back side of it. Also comes in with a filter. So really there's only two ways this system can fail. A, it can plug up and get all nasty and deteriorate. It looks like this one had a compressor go through it because I see a bunch of metal chunks and stuff inside of there. The other thing that could happen is the technician before you put the wrong one in. So this orifice inside of here has to be the perfect size for your system. If you put the wrong orifice in there, you're going to put in too big or too small of a hole, and your whole AC system is going to go down because it's not going to function at the proper pressure differential between the high side and low side. Also has a little filter here to catch foreign particles. On to the thermal expansion valve. So on the thermal expansion valve, this is where the orifice tube would be located. But on this one, we have what's known as a capillary tube. And this capillary tube basically sits down here on the outlet side of the evaporator. And if the temperature on the outlet side of the evaporator is hot enough, then it's going to take the freon that's inside of this capillary tube, and it's going to turn it into a gas, which is going to make it expand, which is going to move a little diaphragm inside of here, changing the output of the evaporator. I got a little video that'll explain that a little bit better. So why don't we watch that for a minute, and then we'll move on.
If we pull apart a thermostatic expansion valve, then we're going to see the following main components. The valve body, which holds the components and has an orifice inside to control the flow of refrigerant. Then we have the diaphragm, which is a strong, thin, flexible material, typically metal, which flexes to apply pressure. Then we have the needle or pin and seat. This moves up and down to restrict the refrigerant's flow path. The spring, which counteracts the force of the needle. And we've also got the sensing bulb and the capillary line, which causes the valve to open or close. As you can imagine, there are a lot of different designs out there for how these valves work. I'm just going to stick with this simple version here to help you understand the basic working principles. So how does it work? Well, as we saw in the real world example, the valve sits just before the evaporator and holds back the high pressure liquid refrigerant from the condenser and controls how much refrigerant can pass into the evaporator. The valve decreases the pressure to allow the refrigerant to boil at lower temperatures. For example, we're used to water boiling at around 100 degrees Celsius, 212 degrees Fahrenheit. That's because most of us live near sea level, so the air around us is compressed by all the weight of the atmosphere above us. However, if we went higher into the atmosphere, say to the top of Mount Everest, then we would find that the water boils at only 70 degrees Celsius, 158 degrees Fahrenheit. And that's because we're higher up, so there's less atmosphere above us to push down on the water, which makes it easier to boil. The boiling is essential for the refrigeration system, as it will absorb the heat from the air or water and carry this away to the compressor. Also, just remember that the refrigerant has a much lower boiling point than water. The high pressure liquid is forced through a small orifice, which causes a pressure reduction, and as it passes through here, some of it will vaporize and the rest will remain as liquid. It's similar to a water bottle spray nozzle. As you pull the trigger, the high pressure water is forced through the small orifice into a much lower pressurized atmosphere. This causes the water to become part liquid and part vapor. This mixture of liquid vapor refrigerant is sprayed into the evaporator, where it will absorb heat from the air or water which surrounds the pipe. In this example, the fan is blowing air across the evaporator. As the refrigerant passes through the evaporator and is exposed to more thermal energy, it will cause it to undergo a complete phase change and will then become a saturated vapor towards the end of the evaporator coil. During this change, there will be little to no temperature change because of the latent heat, and instead it will increase in entropy and enthalpy. The refrigerant will continue to pick up thermal energy, and when it does this after the phase change has occurred, it will then start to increase in temperature. This superheats the refrigerant vapor, and the sensing bulb of the expansion valve is monitoring this temperature to control the refrigerant. So let's have a look at an example. Let's say the cooling load increases. This will cause more refrigerant to evaporate, and the superheat will increase, causing the refrigerant temperature to increase at the evaporator exit. We need to decrease the superheat, and we can do that by allowing more refrigerant to flow into the evaporator. So the pin will need to open more to let the refrigerant pass through. Inside the sensing bulb is a small amount of refrigerant which is separated from the rest of the system and constrained in a closed system to the area of just the bulb, the capillary tube, and the power head. The sensing bulb detects the temperature increase, which causes a small internal reservoir of refrigerant to also boil and evaporate. Because the refrigerant is constrained to a small area, it will cause the pressure to increase, and this pushes along the capillary tube up to the top of the expansion valve. This pushes down on the diaphragm, and that pushes down on the pin, which compresses the spring and allows more refrigerant to pass through the orifice. The valve will adjust to find the correct position so that the force on the diaphragm is greater than or equal to the force of the spring pushing in the opposite direction. This allows the correct amount of refrigerant to flow, which decreases the superheat refrigerant temperature at the outlet, and the sensing bulb detects this and equalizes it. If the cooling load then decreases back to normal, the superheat temperature will reduce. The sensing bulb will detect this and will begin to reduce the refrigerant evaporation in its chamber. The refrigerant in the capillary then flows back towards the bulb and the main valve begins to close. The superheat temperature will also start to rise as this happens. Eventually, the valve equalizes out and the correct amount of refrigerant will flow through to match the superheat settings. Now, all of this happens automatically using this type of valve, which is why it is so popular. There are other electronic versions of this valve which can provide even more precise control, but we'll look at that in a later video. So what happens if the valve fouls or the wrong superheat settings are used? Well, if the valve didn't react to the superheat, it could let liquid refrigerant pass straight through and into the compressor. Compressors hate this because liquids can't easily be compressed, and so the compressor will, well, maybe not to that extreme, but the liquid will damage it, so make sure the superheat setting is correct.
Alright, and the final system I want to talk about is the H-block. This is the newest system, probably the most common used today on all the newer equipment. The H-block system is basically, the gateway is right here and it's controlled by a diaphragm that's controlled by the outlet pressure. So it's no longer controlled by temp as much as pressure. I got a little bit better diagram on the next page here. Alright, so here's our high pressure coming in. Comes in through this itty bitty tiny little orifice hole right here. Goes out through the evaporator where it goes through a state of change and it goes back into a gas. That gas pressure pushes up on this diaphragm in here. And if you have an extremely high gas pressure, right, it's going to push up on this diaphragm, which is going to pull this needle up, which is going to close this hole. Now the compressor that's on beyond it is going to pull a vacuum in all of this, and therefore that pressure is going to start to drop back down, in which case that diaphragm is going to lower itself back down, and that needle is going to lower itself back down, therefore opening the hole and allowing more Freon to travel through. Very simple design. Took us a few years to get to it, but it is a very efficient design. Pretty much the biggest area where this system fails is going to be at this small orifice. If debris or something gets stuck up inside of there, it can get stuck open or closed, in which case you would have to replace it. Stuck closed, pretty simple. You got a major vacuum over here. You got a very high pressure back over here. Eventually your compressor can't keep up. And that moves us on to the evaporator. So the evaporator is the component. It's usually located inside the cab or right outside of the cab, the inside of the cowl of a truck or up in the hood compartment above a tractor cab. The evaporator core, this is the coldest part of the entire AC system, right? Because we just went through that expansion valve that caused it to go from high pressure to low pressure. That's going to cause it to start to get extremely cold. As it travels through here, it is going to absorb the heat. We got a blower motor blowing air through it, right? The heat that's inside of that air is going to get attracted into that Freon, and so we're going to get a state of change once again, and all the Freon that's inside of here is going to evaporate and become a gas. That's highly important because if it doesn't become a gas, the next component it travels through is going to be the compressor, in which case compressors do not like fluid, and they have a tendency to blow up because fluid doesn't like to compress, at least not in a standard AC compressor. Thermostat. Thermostat is located inside of the evaporator or right beside the evaporator. Its entire job is to measure the temperature of the air that is blowing through that evaporator. So what temperature are we at that exact same point? Because if we're too cold, then potentially we're going to freeze something up and we need to turn our compressor off so that it'll stop pulling the vacuum in that cold side. If it's too hot, then we need to turn that compressor on. That way we can pull more of a vacuum, right? Get that bigger pressure differential, get it colder. That way our air blows colder out. So it's literally just a temperature sensor that turns the compressor itself on and off by actuating the clutch that's on the compressor electronically. So we have our temperature lead right here. Typically have a couple wires coming off of this thing that run into the control of the compressor clutch. These thermostats, they can go in a few different places. One of the most common is you literally count an exact number of fins up the evaporator and you shove it down into the fins. Another common place is sometimes they'll lay in the front of an evaporator, but you need to follow your OEM chart because that can really change based upon what you're working on. So make sure you follow your OEM chart. If you put it in the wrong spot, your compressor is going to cycle at the wrong time and your AC system is not going to work. So make sure you look and see what your OEM says. Thermostats are not the only control for a compressor clutch. We also have binary and trinary switches. Binary switches are a simple, normally closed switch. So in other words, electricity is allowed to flow through them as long as the pressure that is inside the system is correct. So we can put these on the high side, right? And if the pressure ever gets too high, it would open this switch and therefore either cut the power or the ground to the compressor clutch and shut the compressor off. Or we could put them on the low side, the vacuum side, and if the pressure ever gets too low, then it would open up the switch and it would immediately shut the compressor off. So more or less, they're just kind of a safety switch. If you have a compressor that's not turning on and off, you know the freon charge is exactly right. One of the first things you kind of want to check, especially if it has binary switches, are the switches. And they're pretty easy to check. So right down here, we got a little wiring diagram, right? So let's say this is power coming in, goes through the switch, and this is the power going out to the compressor. If we think this switch is bad, what we can do is we can put a little jumper wire or paper clip from this wire over to this wire, and if all of a sudden the compressor clutch starts kicking on, then we know for a fact that our switch is bad because we have the right amount of freon, we have our gauges hooked up to the system, we know our pressures are right, and all of a sudden our compressor starts working. It's got to be that switch. On a trinary switch, you can kind of do the same thing as long as you have a wiring diagram, but they also have a third function that they run, and that is they can adjust radiator fins or they could run the fan clutch itself. So if we're sitting at an idle, we have our AC on high, we don't want our truck overheating, we can actually operate the fan through the trinary switch by reading the pressure inside the AC system. It knows the compressor's running, so it goes ahead and kicks on the engine fan, pulls that air through the condenser. That way that condenser can keep allowing airflow to flow through. That way the heat can escape out of the condenser. And finally, we have pressure sensors and or transducers. These are probably the newest of everything. Pretty much Caniclip is about the only one anymore that still runs binary switches or trinary switches. Pressure transducers, they're a pressure sensor. So they actually send a actual pressure inside the AC system back to the body controller, and then the body controller tells the clutch or the engine fan or whatever else whether or not to turn on or off. They're a little bit more of a pain to diagnose for your common everyday person who doesn't have a laptop, but they're much easier to diagnose for a technician in a shop who does have a laptop because they can just hook up to the laptop, they can see what pressure they're reading and immediately know exactly what pressure's in that system. Or if they think the sensor's wrong, then they can hook up a set of gauges and they can compare the sensor to a set of to what the gauges are actually reading, and diagnose the sensor in a matter of seconds. R12 and R134A systems, we kind of talked about this already in our previous Max class. They have different fittings. Make sure if you ever change out a system over to R134A, you replace the fittings. That way the next person knows. And that leads us into diagnostics of this system. So we already talked about temperature differential. I'm going to create a video a little bit later that talks about pressure diagnostics. However, there are a few things I do want to show you now. All right, so a lot of the times over a long period of time of operation, rubber hoses have a tendency to deteriorate on the inside. This is a lot of the time what causes a plug inside of either your orifice down at your H block or your orifice tube, or it can actually cause a plug. See how this right here, let me back it up just a hair further. Right here, we have this hose starting to actually peel back. I have seen it before where this hose will peel back so far that it'll completely plug this entire line right here, and you'll have a hot side over here and a cold side right here, in which case you just replace the line. Otherwise, you always, whenever you're opened up into a system, you want to inspect your orifice tube or your H block or anything like that for little metal, or sorry, not metal, rubber flakes inside of it. Because so your orifice tube, if it was froze over, you want to check it for little rubber flakes of any kind anywhere. If you find rubber, then chances are you got hoses deteriorating. If you find metal, chances are you got a compressor that's deteriorating. All right, leaks. I think I'm gonna, when I do the video later, I'm definitely gonna point this out. However, on all of these fittings, right in here where the hose is crimped in, that's a very common place for it to leak. Anywhere where the hose is hooked up is a very common place for it to leak. Any fittings where there's an O-ring or a seal. Right behind the compressor, the drive pulley for the compressor, there's a seal back in there that leaks a lot. That is probably by far the most common leak that I found while working on an AC system. So shove your sniffer, if you got an AC refrigerant detector, shove that sniffer up inside of here. Refrigerant is heavier than air, so typically you want to go from the bottom, shove it up in through the bottom, but sniff all around it, see if you got a leak up inside of there. Bad refrigerant, too much or too little refrigerant can cause your compressor to blow up. Sends metal throughout the whole system. If you have to replace your compressor, you're also going to be replacing your condenser because it now has metal in it. You're going to be replacing your H block or your orifice tube because it now has metal in it. You're going to be replacing your accumulator or your receiver dryer because it now has metal in it. The only component that you might not have to replace is the evaporator, just simply because it does have to cross through the expansion valve in order to get into the evaporator. However, follow OEM spec on whatever they say. Sometimes they will have you replace it anyway. All right, so every OEM has their own set of guidelines on how to diagnose a system. You always want to follow OEM, especially if you're wanting to get paid because it's under warranty. Follow OEM guidelines. They do change little by little. However, this is a general set. This will get the job done, especially if you're working on it at your house on your own. Obviously, step number one, gather information. A lot of the times when a service writer talks to a customer, they'll find out that the AC doesn't work. That's not enough information. If you go talk to the customer and you find out that the AC works just fine for 30 minutes and then it stops working, that's a completely different story. And so they shut it off, and a couple hours later, and all of a sudden the AC works again. That tells me immediately that that system is freezing up. It's causing an ice block inside the system, plugging the system stops working until that ice block thaws, and then the system works again. And then it freezes up again, so on and so forth. Whereas an AC system just not working could be a leak, and so you no longer have Freon. Two completely different diagnostic paths, all because of talking to the operator and getting more information. Next step, you always want to confirm the complaint. That's always step number two. Check fault codes with the body controller, especially if you have a smart system with pressure sensors on it. If those pressure sensors are reading incorrect, then the compressor is not even going to cycle on or off no matter what. I like to do my walk around inspection typically when I'm confirming the complaint, but if you haven't already done it, you're going to be running the unit for at least 2 minutes minimum at max AC. That way you can get the temperature out of the vent that is closest to the evaporator. That temperature you should see somewhere around 45 to 50 degrees. unless of course it's 120 degrees outside, then quite honestly 70 degrees is probably about the best you're going to get. Um, let's see, where was I? Sorry. Oh, I like to do my walk around inspection right here as well, though. There's a ton of stuff that you need to be checking out. In fact, I think I have that in the next slide or two. We'll talk about that stuff. Confirm that the compressor cycling, if the compressor's not coming on or off, that's going to change whether or not what direction you're going to look. So if the compressor's coming on and it's still blowing hot air, then honestly, I'd be checking filters if I haven't already done that in my walk around inspection. However, if the compressor's not turning on, well, that tells me it's probably not in the filters, the cab filters. It's probably low freon or something along those lines. Confirm all your doors move. You got mode doors, blend doors, blower motor operation. So make sure you got all speeds of your blower motor. Make sure you're pulling air in from outside. Make sure you're recirculating air when you go to max AC on the inside. Make sure you can get air up on the dash panel as well as up on the defrost. You need to check all of that stuff before you ever even start diagnostic. All right, during your walk around inspection, one of the big things you want to check are belts. Obviously, if you're missing a belt that drives your AC compressor is not going to be able to do any work. So check your belts real good, make sure they're not cracked, pitted, loose, make sure they're tight, the pulley's good and tight. Make sure the compressor's not loose on any of its mounting or making an excessive amount of noise because it's destroyed on the inside. Check to make sure your clutch is actually engaging, disengaging. It's not slipping, anything along those lines. Let's see, check your condenser, leaking, cleanliness. A lot of the times on big leaks, you can actually see them. They'll have oil dripping out of them, something along those lines. Make sure they're clean, not full of dirt. That's where you're going to see that 20-degree temperature drop instead of the 50-degree temperature drop if they're full of dirt. Receiver dryer, pretty much everything. You're doing a visual inspection on every single component on here. You're checking for cleanliness, you're checking for mounting, you're checking for absolutely everything. Leaks are very common. Let's see, is there anything in here I need to point out? Odor. Odor is one yet you might want to look at. If you got odor inside the cab while the AC is operating, it's a very good chance that your evaporator is actually leaking. Another possibility is the drain on the evaporator. If your drain froze over and got plugged up, then that water is building up on the evaporator instead of draining out like it's supposed to. And therefore, you're going to start to get a kind of a musty smell, dirty, nasty, musty smell inside of there. Let's see. Obviously, check your electrical as well, things like that. This is a good thing. However, follow your OEM. They most likely also have a list almost exactly like this, but use theirs. HVAC pressure analysis. So the AC system runs off a pressure differential, right? So therefore, it makes sense that as a technician, you probably want to use pressures to diagnose the system. About the only time you're not going to use pressures to diagnose the system is when it's an electrical fault or when it is an obvious plug and you can see something on the high side frozen up. Other than that, you're going to be hooking up your pressure gauges. You're going to be reading what your pressures are on both sides, which leads me to this screen. So this top chart here, you cannot use these pressures at these temperatures to diagnose the next unit you work on. This is just a general idea of what most OEMs have available for the specific truck you're working on. So this pressure right here at 110 degrees Fahrenheit at 50 degrees on the low or 50 psi on the low side may be exactly perfect, but only for the unit that this chart was made for. It's not going to work across the board because these pressures are going to change based upon how much capacity of freon is in the system. They're going to change at what temperature it is outside, what elevation you're at. So in other words, what's the barometric pressure pushing on the system. So there is no general chart for all equipment out there. It's going to change from make to model to everything else. However, this will give you a pretty standard idea of what you're going to be looking at. 20 to 25 to 50 to psi on the low side, 100 to 400 on the high side. This is with the compressor operational. Heated up. You've already gone up through the warm-up procedure, all that fun stuff. You compare it down to the temperature. So if it's 70 degrees outside, I'm reading 35 psi and 145 psi. I'm actually looking pretty good. But if I was reading, let's say 10 psi and 10 psi on the low and high side, well, then now I have a problem, don't I? So let's go down here. I'm low on both sides. Let's go down here to this little chart down here. We got a low on the low side, low on the high side right here, low refrigerant charge. Well, that makes sense. If I don't have any refrigerant in the system, then I'm probably going to be low on pressure. However, that is not the only possibility. If we come down here, we'll also notice we got 3 more low lows. If the expansion valve is stuck closed, if the orifice tube is plugged, or if we have a high side restriction. So the first thing I would probably do is see how much refrigerant I have in the system. If I have a high amount of refrigerant in the system, then it's probably going to be one of these down here. If I have a low amount, well, then I found my problem. So if I did have a high amount, where would I go? Well, expansion valve versus orifice tube, that's a matter of what system I have. And a high side restriction is once again going to cause that pressure differential where it shouldn't be. So we could use our hand to feel the temperature difference between where the plug is. If there is a big temperature differential in there, then we for sure have a high side restriction, and we know how to fix that, replace the component. Finding leaks. So if you do have a low refrigerant charge, you got low pressures on both sides, low and high, there's a few different ways you can find leaks. One of the most common ways to find leaks, honestly, is probably to charge the system back up with Freon and use this little sniffer tool right here in order to go sniff out where the Freon's leaking. I know a lot of shops that do this. However, Freon is extremely expensive compared to a lot of other gases that we could use. At our shop, we actually, instead of charging it back up with Freon, we charge it up with nitrogen. And then our sniffer will actually pick up nitrogen as well. And we can find the leak that way. Or we can spray it down with bubbles and look for the bubbles to form up and find the leak there. Now, the bubbles, they work for generally pretty large leaks where the sniffer is going to work for small leaks. Finally, if you still haven't found the leak, you can use UV dye, which you just inject the AC system with UV dye, run the system for 10-15 minutes, let that stuff mix up inside the system, and then take a black light, shine it all over, and wherever you see a nice bright shiny light material from the UV leaking out, that's where your leak is. When you charge up a system with nitrogen, typically most operating systems, they run around 300 psi. However, you don't really want to start that high. I typically start at about 200. If I don't find the leak, I'll go up to about 250. Sometimes I'll bump up to 300 psi. However, if I'm up to that high, I'll usually go get the refrigerant leak detector and start using that thing instead of bubbles. It's a little bit more accurate. It can read smaller leaks. What is it, like 15 hundredths per year or something like that? It's crazy how much those can pick up. You can also nitrogen test individual components. So if you pull the condenser off or the evaporator out, you can hook up nitrogen to them, plug up one end, hook them up, dip them down into a water tank, look for bubbles that way. Leak detectors. One thing about these leak detectors is that they are so finicky. I mean, they're so accurate, really, that it doesn't take a whole lot to mess them up. So if you were to bump the tip on a piece of metal, or if you were to go over a piece of, maybe you just sprayed the system down with a bunch of bubbles, if you were to go over that area, it might actually set this thing off. A lot of the time what I like to do with the sniffer is I'll go over area, let's say the Schrader valve on the high side, and if it sets it off, then I'll leave that area and I'll go check the condenser. I'll come back in a minute or two and I'll check that high side valve again. If it sets it off again, then I'll leave again. I'll go check the receiver dryer and I'll come back, and if it sets it off again, then I know my leak's there. But if it just sets it off once, don't worry about it, because that's probably not where your leak is. It's just the detector itself went off randomly because you tapped it or you got a little bit of debris in it or something like that. You don't want to move those refrigerant detectors very fast. You're looking at moving them about an inch or two a second. I mean, it's a nice slow space in order for it to pick up the freon that's leaking. You never want to touch the surface. Keep the tip of that thing about a quarter inch away from the surface. If you bump it, it will most likely set it off. And always remember that refrigerant is heavier than air. So in other words, refrigerant will sink. So if you're wanting to test a component, test it from the underside, like that compressor clutch seal that we were talking about. Go in from the underneath. That way the freon leaks down towards the sniffer itself. Temperature testing. We've talked about this a few times. Here's kind of a general idea. You're going to lose 20 to 50 degrees right here through the condenser, 2 degrees through the receiver dryer. You're pretty much going to lose all the temperature through the H block. And then the evaporator, it can change. You can be high on the low side or you can be high on the high side. In fact, actually, I think I have this here. Yeah, we split it up by components. All right, so 20 to 50 degrees. If it's only 20 degrees, chances are the fins are plugged. Go clean them out. If it's 100 degrees, then you got to plug inside the condenser itself. Replace the condenser. On the evaporator, on this side of things, it changes quite a bit. So the suction line is, if the suction line is more than 5 degrees warmer than the high side, then you have a low system charge or restriction. So if this side over here is 5 degrees warmer than this side over here, you need more freon. You shouldn't have any temperature drop across here. None. In fact, a lot of the times, back before we knew exactly how much freon to put in every single system, what we would do is we would put our hand on this line and put our hand on this line, and when they felt like they were the same temperature, we stopped putting freon in the system. They should be the same temperature. However, if we're 5 degrees warmer over here, then we need more freon. If we're 5 degrees colder over here, then we probably put too much freon in, or somebody put the wrong orifice tube or the wrong orifice size on the inlet. Always stick a thermometer inside the vent closest to the evaporator. You need to know what temperature is actually coming out of this system. Like I said, it's pretty standard to be around, probably about 50 degrees coming out of the vent. However, if it's 110 degrees outside, I wouldn't be surprised if you don't see that needle up here at the just below the 70 mark. AC can only do so much when it's extremely hot outside. Refrigerant recovery stations. I'm going to show you how to work one of these in another video, so I won't go into them too much right now. Big thing you need to know, they have to be certified by the EPA, they have to be inspected, they have to be serviced, they can't have any leaks, things like that. But I'll talk about actual operation in a later video. Manifold gauge sets, pretty standard sets. They do have two different sets for R12 and R134A, different fittings, so you need different gauges. One thing, if you're ever charging an AC system, you don't have that big $3,000 machine that we saw in a couple previous slides ago. All you have is a set of gauges. You always want to be charging on the low side. You can start your charge on the high side if you want, but chances are it's not all going to go in there. So you charge on the low side, the vacuum, then you start the truck up, and the vacuum inside the AC system itself will actually pull the freon out of the tank. If you're charging on the high side, that's all right, but never, ever start the truck, because then all of a sudden the pressures are going to shoot up here to this 300 range, and they're going to probably blow up your gauge or something, or one of your lines, probably one of your hoses that you're hooked up to the truck with. And that goes even more importantly, if you're ever charging an AC system with one of those aerosol cans that you buy from AutoZone or O'Reilly's or something like that, never, ever, ever hook one of those things up to the high side. It will blow up in your hand. Never open the high side hand valve with the system operating. See, there it is right there. We're talking about high pressures, not a good idea. Altitude will change the chart. Pressures, obviously, we talked about that as well. Traders, very common leak place. That's the ports where you hook up your high and low side lines in the AC system. It's just a standard bike trader. I mean, it's not very different compared to one of those. Spring operated, so they do leak quite a bit. Whenever you're doing a leak test, always shove your sniffer down inside of them, make sure they're not leaking out or spilling full of bubbles or something. Obviously, they're also designed so you can't hook up an R12 to an R134 system. And that's still talking about different fittings between the two. Weighing a refrigerant canister. Once again, if you don't have the $3,000 machine, honestly, even this is a super nice scale, nicer than what you need. You can go get a bathroom scale. You can put a bathroom scale under here, and as soon as you lose 3 pounds of Freon on the bathrooms, or the bathroom drops 3 pounds, the bathroom scale does, then you know that you've put 3 pounds of Freon in the system. One important thing to note, though, is if you're trying to fill the truck up with 3 pounds of Freon, then you need to shut the tank off itself when you're probably at about 2.5 pounds of Freon, because there's probably half a pound of Freon in the line that's going up to the truck. So you continue to allow it to run, but you shut the tank off so it's not still charging Freon. Every OEM is going to come with a flow chart. If you find it, it's going to give you a step-by-step, especially if you want to get paid by warranty. Just make sure you're following the steps appropriately. This is an HVAC unit. So right inside here, we have our blower motor. Right here's our control head up in the dash. Looks like we have most likely that's our recirculation blend door. Our recirculation actuator that determines whether or not the air comes in from outside or if it's recirculated in the cab itself. Our evaporators back inside of here. Right here we have, most likely this is, I'm going to say, yep, this one's going to be our directional, so it'll determine what goes up to the defrost actuator and what comes out the dash, whereas this one is our blend door, so it's going to determine, are we going to flow our blower motor air through the evaporator that's down inside of here, or are we going to flow that air through our heater coil that's down inside of here and blow out hot air, right? And that's it, guys. That's all we're going to talk about. Watch for the videos that'll be coming up for diagnostic on an actual working running unit. I'll get those released as soon as I can.